In this video, we want to take a look at the precise definition of a limit. In a previous video, we actually discussed an informal definition of a limit, and for the purposes of this class, that informal definition will be fine. But we are using several limit laws and theorems related to limits in this course, and to actually prove those limit laws, we have to use a more precise definition of a limit. So while we're not going to go through a lot of those proofs in this class, I do want to give you some background to show you how those proofs might actually be done. So we do want to cover this precise definition of a limit. And we'll do so in this video, and then I'll have another video as well with some more examples. All right, so let's get started with this actual definition. So we're going to let f of x be defined on an open interval about x naught, except possibly at x naught itself. And that's okay, because for a limit, we don't care what happens exactly at x naught. We only care what happens right around that value. So we say that the limit of f of x as x approaches x naught is the number L, and we write the limit as x naught as x approaches x naught of f of x is equal to L. If, and now this rest of this is the conditions that must be met, and that is that if for every number epsilon greater than 0, there exists a corresponding number delta greater than 0, such that for all x within this interval, so 0 less than absolute value of x minus x naught is less than delta, we have that f of x, the absolute value of f of x minus L, will be less than epsilon. So again, I'm going to repeat. The real condition is that we will be given some epsilon greater than 0, and we must find a delta that gives us x values within a range, that for every x value in that range, the y value will be very close, in fact, a distance less than epsilon from the value L. If that is true for every epsilon we could possibly choose, when epsilon is a positive value, then this limit exists and it is equal to L. And that's our precise definition of a limit. So we're going to do several examples and a couple of proofs. So let's start with our first example, and that is to show that the limit as x approaches 1 of 5x minus 3 is equal to 2. So here, x naught is equal to 1, f of x is equal to, so x naught is equal to 1, f of x is equal to our function, 5x minus 3, and the L is 2. So what must happen is for any given epsilon greater than 0, we must find a delta greater than 0 such that for all x in the interval 0 less than the absolute value of x minus 1 is less than delta, this implies that f of x minus 2 will be less than epsilon. Well, in this particular problem, we have an easy way to solve that, and that is to work backwards on this inequality here. So let's write this out with f of x plugged in. What is our f of x here? That is 5x minus 3. And so we have the absolute value of 5x minus 3 minus 2 is less than epsilon. So then 5x minus 5 absolute value of that is less than epsilon. Actually, let's write it out like this. This is equal to 5 times absolute value of x minus 1. And we want this to be less than epsilon, or, in other words, the absolute value of x minus 1 is less than epsilon over 5. Okay. So what happens if we take delta equal to epsilon over 5, right? Epsilon is some positive value. So epsilon divided by 5 is some small positive value. So we let delta equal that, because we need delta to be a positive value as well. And if we let it equal to epsilon over 5, it's still a positive value. So if we let this delta equal epsilon over 5, then if 0 is less than the absolute value of x minus 1 is less than delta, which is our given statement, part of our given statement, then what do we have? Well, we have the absolute value of 5x minus 3 minus 2, which, what was this equal to? That was our absolute value of f of x minus L. Well, this is equal to absolute value of 5x minus 5, which is equal to 5 times absolute value of x minus 1, which is less than 5 times delta, because absolute value of x minus 1 is less than delta, right? Well, this is equal to, because delta, we're picking delta to be epsilon divided by 5. This is 5 times epsilon over 5, which is equal to epsilon. So what we've shown here is that if with this choice of delta, for any x in this range, we are in this interval, we have that f of x, the absolute value of f of x minus L is, and through this string of inequalities, we get a less than epsilon, which satisfies the exact conditions that we were trying to show. So this is actually the proof that the limit as x approaches 1 of f of x minus 3 is equal to 2. All right. Now we're going to do another example in this video, and that is to complete 2 simple proofs, very simple proofs here. We want to prove the limit as x approaches c of x is equal to c. So what happens is we let epsilon be greater than 0 is given. So we just pick some epsilon greater than 0. We don't pick a specific one. We want this to be arbitrary. So we're just defining epsilon to be some small positive value. And if that is given, we must find delta greater than 0, where for all x within this interval, this implies that the absolute value of x minus c is less than epsilon. Okay. All right, x minus c is what we're approaching here, less than delta, and we want this to imply that f of x minus L is less than epsilon. But notice here, f of x, our function is just x, and L, the thing that we're approaching, is c. So we plug those in, and we get that. Well, guess what? This is really easy. Just pick delta equal to epsilon. If delta is epsilon, then given this statement right here, we have that the absolute value of x minus c is less than epsilon now, since delta is epsilon, and that's exactly what we wanted to show. In fact, we could have chosen any delta less than epsilon, and this would have satisfied our statement as well that we must show. But here, just delta equal to epsilon is the easy choice. Okay. This was actually part A of this example. We're going to do a part B. We're going to prove that the limit as x approaches c of the function k is equal to the limit k, where k is some constant. Okay. So again, where we start with the statement that we let epsilon be greater than 0. We must find delta greater than 0 such that for all x where 0 is less than the absolute value of x minus c is less than delta, this implies that the absolute value of f of x minus L, but f of x is k and L is k, so this is less than epsilon. Well, this right here is 0. That's always less than epsilon by the statement we were given at the beginning. So this is true for any delta that we choose. So we can pick any delta and this will be satisfied. Oh, there we go. So that actually completes our proof. And that'll actually end this first video as well. We'll have a second video with a couple of more difficult examples.